Hello and welcome to our video on Equilibria and Reversible Reactions. If a reaction is reversible, it means that it can go in both directions. In other words, the products of the reaction, by that we mean the right-hand side, can themselves react to produce the original reactants, in other words, the left-hand side. So they can be represented like this. So if we have A plus B reacting together to make C and D can then react together to go back to being A plus B. This double arrow is the symbol for a reversible reaction. Now, eventually, every reversible reaction reaches something called equilibrium, which we will come to in a moment. But what we can do, and this is what this topic is about, is that we can change the conditions of a reaction, such as the temperature of it or the pressure of it, and we can then change the overall direction that the reaction is going in, and therefore we can make more of one side than the other if we want to. And that's what we learn about, is how we go about doing that. So, if a reversible reaction takes place in a closed system, a closed system just means one in which nothing can escape. So everything that you make stays within that same reaction vessel, which means that it can then react with itself to then go back to making what we started with. And in that situation, with a reversible reaction, a state of equilibrium will always be reached. Equilibrium is when the amounts of reactants and products reach a balance. So the left-hand side and the right-hand side reaches a balance, and their concentrations stop changing. So this is how it happens. As the reactants, the left-hand side originally, react, their concentrations fall. So we start with a lot of them, the amount of the reactants falls. And so the forward reaction slows down. So if we start with lots of A and B, initially it's a really fast reaction, but then gradually as A and B gets used up, it starts to slow down. However, as more and more products are formed, so we start to make more of C and D, and they start to react together, then the backwards reaction speeds up. So when we say backward reaction, we mean C plus D turning into A plus B. The forward reaction is A plus B turning into C plus D. So as the reaction progresses, we start to make more of C and D. As we make more of C and D, they start to react to make more of A and B. But then as we get more of A and B, they start to react to make more of C and D. And so as you can see, eventually what happens is that the speed at which C and D are reacting to make A and B becomes equal to the speed at which A and B are reacting to make C and D. And so there's no overall change, and we reach what we call an equilibrium. So eventually, the forward and backward reactions will be taking place at the same rate. That is what equilibrium is. Make sure that if you define equilibrium, you mention the word rate. It's not about more of one side than the other, or the amounts that's being produced is equal. It's the speed with which we're going forwards and backwards that's become the same. It may mean that we have slightly more of one side than the other, but the point is that those concentrations, those amounts, stop changing because the rate at which the reactions are going becomes the same. So both reactions are still happening, but the overall effect is nil, because the two reactions now cancel each other out. So we're not making any more of one side or the other side now. We've reached what we call equilibrium. When a reaction's at equilibrium, it doesn't mean that the amounts of reactants and products are equal, as I said. It could be that the equilibrium actually lies slightly to one side, which means that the concentration of the products is greater than that of the reactants, or the concentration of the right-hand side is bigger than the left-hand side. Similarly, the equilibrium can lie to the left, where the concentration of the left-hand side is bigger than the right-hand side. But equilibrium is all about the rate at which the forward reaction and the backward reaction are going. It takes a little while to get your head around it, but make sure you understand the definition of it. So, here is an example of a reversible reaction. The thermal decomposition of hydrated copper sulfate. There is the symbol for a reversible reaction. If you heat blue hydrated copper sulfate, it drives the water off and leaves you with white anhydrous copper sulfate, and the water essentially has evaporated. This is endothermic. We're going to come to endo and exothermic in a while. But it's clearly endothermic in that direction, okay, because that's one where You heat it for that reaction to take place, and it takes in heat. If you add some water to anhydrous copper sulfate, to the white powder, then we go back to the hydrated copper sulfate, and this reaction gives out energy, so it's exothermic. Every reversible reaction is endothermic in one direction and exothermic in the other. So in this case, it's endothermic that way and exothermic the other way. You will usually be told this in the question, although some harder questions sometimes require a little bit more knowledge. But just so you understand that that's what we mean here. One way is endothermic, the other way is exothermic. Another reaction is the thermal decomposition of calcium carbonate. Here is the equation, there is the symbol for a reversible reaction. The decomposition of calcium carbonate to form calcium oxide and carbon dioxide is an endothermic reaction. So we heat this up and we produce these two. If we cool these two down, then they react together and form back to calcium carbonate. Okay, so in this case, it's endothermic that way and exothermic that way. Now, the most important part of this topic is this principle. Le Chatelier's principle is the idea that if you change the conditions of a reversible reaction that's at equilibrium, you can alter the yield. The yield is the amount of products or reactants that we use. So we can change the yield so that you end up with more of the products that you want. In most chemical reactions, we want a particular product. That's why we're doing it. But if the reaction is reversible, the problem what we have is that the products that we're making can sometimes react together and go back to what we started with, which we don't want. So with most reversible reactions, we want to get more of one product than the other, more of one side than the other. And this principle tells us how we can do that. So you need to understand how changing the temperature, pressure, or concentration of the reactants affects the yield. Again, yield is how much of a product we actually get. So let's start with temperature. All reversible reactions, as we said, are exothermic in one direction and endothermic in the other. If you raise the temperature, the yield of the endothermic reaction will increase. So if the endothermic reaction is that way, okay, so if we've got a reversible reaction where it's endothermic in the forward direction, then if we heat it, it means that we will increase the yield of this side. In other words, the endothermic direction side. If you reduce the temperature, it will favour the other side, the exothermic side. Okay. Another way to think of it, to keep it simple, is if you increase the temperature of a reversible reaction that's at equilibrium, we get more of the products that are in the endothermic direction. So if I heat up this reaction, I'll get more of that product because that's the way the endothermic direction is. If the endothermic direction is this way, then heating it would give us more of this product. So that's the easiest way to remember it. If you increase the temperature, you get more of the endothermic direction. And that will help you answer pretty much any question on this topic. So, the reaction below is used to make sulfur trioxide. It's exothermic in the forward direction and endothermic in the reverse direction. So before we even read on, as we said, if you increase the temperature of a reversible reaction at equilibrium, you will favour the endothermic side. So if I increase the temperature of this, I will get more of these two. Okay? If you increase the temperature, the endothermic reverse reaction will be favoured and absorb the extra energy. This would result in a higher yield of the left-hand side. So increasing the temperature gives us more of that side. If we decrease the temperature, we'd get more of the other side. It's just the exact opposite. Okay, so trying to remember one of those is the best way to do it. Increasing the temperature, you get more of the endothermic side. So therefore, if you decrease the temperature, you get less of it and you get more of the other side. It's quite easy to remember that way. Pressure. Changing the pressure affects reactions where the reactants and products are gases. So this tends to only apply to gases, but when you get a question on this, then it will be a reaction involving gases. Raising the pressure favours the reaction which has fewer gas molecules. Lowering the pressure favours the reaction which produces a greater number of gas molecules. Now, to work out the number of molecules, all we do is we count the big numbers in the balanced chemical equation. Let's see an example of this. So, here is a chemical reaction that's used to make hydrogen gas. Right, and let's count the number of molecules here. So, we have a methane molecule here. There is a 1 there, even though it doesn't say a 1. There's a water molecule there, 1. there is 1 carbon monoxide molecule there, and there's 3 hydrogen molecules there. So remember, if there's a big number there, then that's how many molecules there are. If there isn't a big number there, there's only 1. So on the left-hand side, we have got 2 gas molecules. On the right-hand side, we have got 4 gas molecules. So just remember the rule. If you increase the pressure, it favours the side with fewer gas molecules. So if I increase the pressure of this reaction, because there are fewer gas molecules on the left-hand side, I'll produce more of the products on this side. And if I decrease the pressure, I'll get more of the products on the right-hand side, because there are more gas molecules on this side. Okay, so if I wanted to produce hydrogen in this reaction, I'd have to keep the pressure very, very low, because the lower the pressure, the more of that side I'm going to get, because it's got more gas molecules. All we're doing is counting the big numbers at the front and remembering the rule that fewer gas molecules is the side that we favour if we increase the pressure. And then concentration. If you change the concentration of either the reactants or the products, the system will no longer be at equilibrium. It will then respond to bring it back to equilibrium again. And so, just to be clear, if this is the reversible reaction, where we've got a left-hand side and a right-hand side, okay, if I increase the concentration of this side, okay, so if I get more of the left-hand side, what will happen is that these will start to react faster, because now there's a higher concentration, and we'll end up using this up and producing more of the product until it's at equilibrium again. So it will always balance out, because if we add more of one side, it will just use up that extra until everything's balanced again. If you decrease the concentration of a product, so if I have less of this, for example, then all that will happen is that we will start to make more of that side. This reaction will increase, and so we'll end up back to where we were. So if you decrease the concentration of a product, the system will then try to increase it again by reducing the amount of reactants. So it will try to use up more of this side until everything is balanced again. So that's all that happens. It is obvious if you just step back. If you have a reversible reaction that's at equilibrium, if you add in more of one side, then we'll just get a faster reaction on that side, and then we'll produce more of the other side until everything's balanced again. So we're going to see this reaction a little bit more in a moment, but nitrogen and hydrogen can react together in a reversible reaction to form ammonia through something called the Haber process. If the concentration of nitrogen or hydrogen is increased, if I put more of this in, then we're going to favour the forward reaction. It will happen faster, so we'll start making more ammonia until it's balanced. Similarly, if I lower the amount of ammonia, then again, there will be less on this side and more on this side, so we'll favour the forward reaction and again produce more ammonia. So just understand what happens when you change the amounts of either of the sides. And that takes us on to this Haber process again. As I say, it's used to manufacture ammonia, which is used in fertilizers and cleaning products. So this is the word equation, this is the symbol equation. Now I can tell you, even though it doesn't say it here, that this is endothermic in this direction. Okay, and therefore exothermic in the other. And as you can see, if we count, there are 4 molecules on this side, 1 there and 3 there, and 2 on the other side. So before we even go further, you should understand what happens when I increase the temperature or increase the pressure of this reaction. If I increase the temperature, it favours the endothermic direction. So if I increase the temperature here, I'll produce more nitrogen and hydrogen, which is actually not what I want to do, but that is what would happen. If I increase the pressure of this reaction, I'll get more ammonia, because there's fewer gas molecules on that side. So, the problem with what I've just said there is that the ideal conditions, I suppose, if I wanted to make lots of ammonia, is to have a low temperature. As I said, a high temperature favours the opposite direction. It favours those two. We don't want that. We want more ammonia. So we want to use a low temperature, and we'd want to use a high pressure. They would be the ideal conditions here, because that would give us more ammonia from temperature and from pressure. The problem with both of those things is that, as we know, a low temperature results in a very slow reaction. We might get more ammonia, but it would happen very slowly, to the point where it might be too slow for it to be commercially useful. And so what we do is we have a balance. We choose a slightly higher temperature than we need to, so that it still happens quickly, and we still get a reasonable amount of ammonia, even though we could get more ammonia by lowering the temperature. It would just happen a bit too slowly. And similarly, whilst a high pressure is great, a high pressure can be quite expensive because you have to make the reaction vessel and make it be able to handle high pressures and not explode. And so that can cost quite a lot of money, to the point where, again, it could be too expensive to use a high pressure. And so we use a slightly lower pressure because then it still works out cheaper. So all of this is about balancing the amount of ammonia we produced, or the amount of product that we want, and how quickly and how cheaply we can do that. So all of these things in real life is a balance. So as with all industrial processes, the cost and availability of reactants and energy are a factor in deciding the appropriate conditions. And so we have to find a compromise with the temperature and pressure between how much ammonia we're going to get and how quickly we're going to get it. So we just have to balance those things out. Yes, perfect world, we could use a very low temperature and a very high pressure, but that doesn't always work. So this is just explaining what we've just said, that in the Haber process, the forward reaction is exothermic. So forward reaction is that way. So that way is exothermic, and the other way is endothermic. And so, if we increase the temperature, we'll actually move the equilibrium the wrong way, away from ammonia and towards the left-hand side of nitrogen and hydrogen. And so, the yield of ammonia would be greater at lower temperature, but lower temperatures means a slower reaction. And so, we increase the temperature a bit anyway. The 450 degrees C is a compromise between the maximum yield and the speed of reaction. Okay, and so we get quite a lot of product, but we just get it a bit quicker. And similarly, as we saw with this, higher pressures favour the forward reaction because there's 4 molecules of gas on the left-hand side and 2 molecules on the right. Just to show you that again. So increasing the pressure favours this direction because there are fewer gas molecules on the right-hand side. And so this moves the equilibrium towards ammonia and away from nitrogen and hydrogen, which is what we want. So higher pressures increase the yield of ammonia. Okay? The pressure is set as high as possible to give the best percentage yield without making it too expensive to build. It'd be too expensive to build a plant that would have very, very high pressures. Even though we'd get more ammonia and it would happen quickly, it would just be too expensive, and so it wouldn't be worthwhile. And so the 200 atmospheres is, again, a compromise between cost and yield of ammonia. And lastly, in that Haber process, we also just add a catalyst. And the iron catalyst, as we have seen before, makes a reaction go faster, but it doesn't get used up, so it doesn't change the amount of products and reactants. So it doesn't actually affect how much is produced. It just happens more quickly. And without the catalyst, the temperature would have to be raised even further to get a quick enough reaction. But then, as we saw, higher temperatures result in less yield of ammonia. So having that catalyst helps to solve that problem a little bit. It essentially reduces your energy costs and ensures that we still get quite a lot of ammonia being produced. So it is quite an important part of this process. So key things to take away from the Haber process is what happens in a reversible reaction when we increase the temperature and when we increase the pressure. When you increase the temperature, it favours whichever direction the endothermic direction is. You should get told that in the question. So the endothermic direction is the side that we produce more of when we increase the temperature. With pressure, we increase the yield of the side with fewer gas molecules. So you should get a balanced chemical equation. Count how many gas molecules are on the left-hand side and how many are on the right-hand side. The side with fewer molecules is the one that the reaction will favour if you increase the pressure. One final thought on this: if the number of molecules on the both sides are the same, then increasing the pressure has no effect on the reaction. It only has an effect if one side has got fewer gas molecules than the other.